Okay, so this was the numerical that we had started yesterday. We had a 220 volt, 500 ampere, 600 RPM, separately excited DC motor with armature resistance of 0.02 ohm and field resistance of 10 ohm. The load torque was given by 2000 minus 2 Newton meter. There were two parts to the problem. In the first part, we had to find the armature terminal voltage and armature current when the speed is 450 RPM. And the second part, the field winding voltage and armature current when the speed is 750 RPM. Now, as you can see in the first part, the speed is less than the rated speed. So we have to go for armature voltage control. Okay. So before we started the numerical, we had found that at the rated speed of 600 RPM, the back EMF is 210 volt. Now, because we are using armature voltage control, so the flux is constant. That is why the speed is, the back EMF is directly proportional to the speed. So we can use the relation E2 by E1 is equal to N2 by N1. So at 450 RPM, the back EMF came out to be 157.5 volt. Now at 600 RPM, the rated torque is given by the rated power divided by the speed, and the rated torque came out to be 1671.12 Newton meter. So as I told you yesterday, we can use either this torque or we can find torque from this expression, T is equal to TL, 800 Newton meter, that will come out. If we are using the rated torque, we have to use the rated current, that is 500 ampere. Whereas if we are using this torque, we have to find the armature current at this torque. Okay? So instead of finding this, we directly go to finding the torque at 450 RPM, and then T2 by T1 is equal to IA2 by IA1. So that gave us IA2, or at 450 RPM, the armature current is 329.12 ampere, and the armature terminal voltage is 164.08 volt. Okay, any questions here? Yes.
No, sir.
Okay, let us now go to the second part of the problem. In the second part, we want to find the field voltage and armature current when the speed is 750 RPM. What was the field voltage when the speed was 600 RPM?
Sir, to calculate the field voltage, sir, can we assume that the previous field voltage is 220 volt?
No, we don't have to assume. It is 220 volt.
Why, sir?
Sir, how to know, sir?
You will apply rated voltage under rated conditions to both the armature winding as well as the field winding. Okay? So if it is a 220 volt separately excited motor, then under rated conditions, 220 volt will be applied to the armature as well as the field. Okay? The field voltage is not separate. Have you ever seen the field voltage as separately given?
No, sir.
Yes, sir, sometime given, sir.
So I have never seen, but if it is given, then it is separate. If it is not given, then this rated voltage is both, or the nameplate voltage is both the armature voltage as well as the field winding voltage. Okay.
So the answer will be the 181.28 volt field voltage and 181.55 ampere.
Yes.
Yes, sir.
Yes. Okay. So if you have solved it, then no need for me to solve it. Is it so? Yes. Yes. Have all of you solved it?
No, sir.
Okay. So because we want the speed here to be greater than the rated speed, which is not possible by armature voltage control, we have to go for field flux control. In other words, we have to decrease the field voltage, decrease the field flux, okay, so that the speed increases above the rated speed. Now, the important thing in this second part, the important thing to remember here is that the flux is no longer constant. So we cannot use the expression E2 by E1 is equal to N2 by N1. Okay, instead, what we have to use is E2 by E1 is equal to phi 2 omega M2. Phi 2 omega M2 divided by phi 1 omega M1. And back EMF is proportional to flux into speed. So E2 by E1 will be equal to phi 2 omega M2 upon phi 1 omega M1, which can be written as, instead of phi, we can take the field current. Instead of omega, we can take N, IF2 N2 by IF1 N1. Okay, is this clear? Yes?
Yes, sir.
How many of these things are known here to us? First of all, let us say we take N1 to be equal to the rated speed, that is 600 RPM. Then E1 we had found out that was, I think, 210 volt, correct? What will be the value of IF1? It will be the field voltage divided by the field resistance, or that is 22 ampere. Okay? So we know N1, we know IF1, we know E1, we know N2. N2 is how much? 750 RPM. Yes, N2 is 750 RPM. And the speed at which you have to find the back EMF. Okay? Do we know IF2?
No, sir.
No.
No, sir.
We also don't know E2. Okay? So there are two unknowns in this equation. So we can find out E2. And if you substitute all the other values, you will get E2 is equal to 11.9318 times IF2. Okay? We take this as equation number 1. Okay? Okay, there are two unknowns, so we need more equations. So one more equation that we have is in terms of the torque. Now once again, torque is proportional to flux into armature current. So T2 by T1, instead of flux, we can have IF2, IA2 divided by IF1, IA1. Correct? Now IF1 was 22 ampere. IA1 was, I think, 500 ampere. Correct? And T1 was how much? 1671. 1671.12 Newton meter. Okay. T2 we can find out. T2 will be equal to the load torque, and at steady state, motor torque will be equal to the load torque, that is 2000 minus 2 into N. N is 750. So this comes out to be
500 Newton meter.
500 Newton meter. Okay. Okay, we don't have IF2, we don't have IA2 है ना. So if you substitute these values, you get one more equation, that is IA2. Okay. If you substitute all these, you get IA2 is equal to 3291.44 divided by IF2. Is this correct, Subhajit?
Yes, sir. I have done in different way that I have taken the IF2 divided by IF1 some means X, and then I have solved like that. I don't calculate the IF2 value.
ठीक है. Okay.
Sir, using the formula U equals to K5 omega, sir,
Hmm.
we calculated it, sir.
Okay. ठीक है. You can do any way you want. है ना? Ultimately, the answer has to be same. ठीक है. And finally, we have B is equal to E2 plus IA2RA. So in this equation, we substitute E2 in terms of IF2 and IA in terms of IF2. And V will be how much?
230 volt.
230 or 220? 220 था ना?
Sir, 220 volt. 220.
Okay, because you are still applying rated voltage across the armature. So you will get a quadratic equation, and solving that equation, you can get the value of IF2. Then from this equation, you can get the value of IA2, and then the field winding voltage VF2 will be simply equal to IF2 multiplied by RF. Okay. So this is how you have to solve this numerical. Okay. So what we learned from that numerical is, if we have power electronic converters based on which we can have a variable voltage DC supply, then we do not have to change the resistance for changing the speed. Okay. If you want to control speed below the rated speed, you will simply decrease the armature voltage. Whereas if you want to control speed above the rated speed, you will simply decrease the field winding voltage. Okay. So we need the capability to control the voltage. Okay. Now the supply might be either AC or it may be DC, and the supply voltage is constant. Okay. So if the supply is AC, then to obtain a variable DC, you will need a rectifier. Whereas if the supply is DC, then to obtain variable DC, we will need a choker. So these two things we are going to study: first rectifier and then choker. Okay. As I have told you earlier also, even today, whenever the supply is AC, the preferred power electronic device is the thyristor. Yeah. Because when the supply is AC, you don't need to commutate the thyristor. It will turn off because of line commutation. Okay. And as yet, still even now, the SCRs are the most reliable devices. The most reliable power electronic device is still the SCR. So for rectifier circuits, you see that still SCRs are being used. Okay. So let us start. We'll take 3 circuits, 2 for single phase and 1 for 3 phase. Okay. Yes.
Yes, sir.
Yes, sir.
Okay, Malhotra is not there in the class till now.
No, sir.
Okay, so the first circuit that we are going to see is the single phase fully controlled rectifier control of DC separately excited motor. Okay. Okay, because it is a single phase fully controlled rectifier, you will be using 4 devices, and all the 4 devices will be SCRs. If you use half control rectifier, then you use 2 SCRs and 2 diodes. The supply is AC. This is the instantaneous positive terminal. Okay. The supply voltage is given by Vs, that is equal to Vm sine omega t. Okay. These SCRs we can number as T1, T2, T3, T4. How do you represent the motor load?
Sir, RLE load, sir.
Yes. So this is the armature resistance, armature inductance, and this is the back EMF. RA, LA, and E. Okay. This is the armature terminal voltage. It is the output voltage of the rectifier and the input voltage to the motor armature. And this is the armature current. Note that I'm using lowercase for VA and IA because these are not perfect DC. Okay? They will change. However, E, we are assuming that it is going to be constant. That is why capital E is used. However, if we are going for transient studies, then E also becomes lowercase. Okay? Any questions? Yes or no?
No, sir.
No, sir. No, sir. No, sir.
No, sir.
Okay. Okay. When drawing the waveforms, on the x-axis you have omega t. Let us say this angle is pi and this angle is 2 pi. Okay. How many possibilities are there of VA?
So continuous and discontinuous.
No. How many possible values of VA can you get in this circuit? Armature voltage. Of course, continuous and discontinuous is there, but what are the possible values of VA in this circuit? Yes.
So based on the firing angle, it depends.
Not based on the firing angle. How many
So
possible
based on the
values?
based on the converter, that either full bridge or semi converter.
Remember the Subhajit, the converter is in front of you.
It's a full bridge.
How many possible values of VA can you get in this circuit? The answer is 3. The answer is 3. What are those 3 values?
0,
Based upon
Vm,
ele-
sin omega t.
VA by 3, 2 VA by 3 and sorry, VM by 3, 2 VM by 3 and VM.
No.
based upon elements, sir. RAL.
So greater than E, less than E, and equal to E, sir.
No. There are 3 cases here.
0,
There are 3 cases here.
0 Vm sin omega t and E.
The first is that T1, T2 are conducting. If T1, T2 are on, what is the value of VA? Yes. If T1, T2
VM sin
are
omega
on, then VA is equal to VS. The second possibility is that T3 and T4 are on. In that case,
Minus.
Minus VS, sir.
No,
VA
VA.
becomes equal to minus VS. Because we are not considering any source inductance. All four devices will not be on together at the same time. Correct? So either you can have T1, T2
Yes, sir.
on, or T3, T4 on, or all four are off. And if all devices are off, then VA is equal to
E, sir.
Yes, sir.
Okay, so these are the three possibilities of the armature voltage. Okay. As far as the armature current is concerned, as Panak pointed out, it can be either continuous or discontinuous. Discontinuous means the current will become zero within a cycle. Continuous means the current will never reduce to zero. Okay. Okay. So let us say this is the supply voltage Vs, this is minus Vs, and this is your back EMF E. Okay, we are drawing the waveform of armature voltage VA. Okay. This angle is theta 1. What is the angle theta 1? Theta 1 is the angle where the supply voltage becomes equal to E. Okay, is this clear? And similarly, this angle where supply voltage will once again become equal to E, that angle is theta 2. Okay, what is the significance of theta 1 and theta 2?
Sir, after theta 1, I1 will flow, and after theta 2, I1 will stop.
कौन था ये? सुमन था.
हाँ.
सुमन, ये जो होता है, this happens only in RE load when there is no inductance. ठीक है? And that too when you have
सर डिस्चार्ज भी
Yes,
होगा
that
sir.
too when you have only diodes. है ना? Because
So you will
Yes,
follow
sir.
to the
because if you are having SCRs, current will not start flowing from theta 1. Current will start flowing when you trigger the SCR. Okay, so that alpha can be greater than theta 1 also. And because you have inductance, current will not become zero at theta 2. It will continue to flow even after theta 2. ठीक है? So क्या बोल रहे थे सुभजीत?
So that's why I'm telling that it will flow after theta 2
Yes.
up to extension angle. Theta.
Yes, up to the extinction angle beta. So what is the significance of theta 1 and theta 2 here?
Sir,
Hmm.
sir, but the extension angle will depend on inductance, sir.
Hmm.
So it means the range is not fixed, sir. We can vary it.
Hmm.
सर सोर्स टू लोड एंड लोड टू सोर्स पावर फ्लो सर
Theta 1, theta 2.
So before theta 1, hello? So before theta 1, back EMF is less. Back EMF is more than Vs.
Yes, that is why the SCRs are. That is why the SCRs are.
Sir, in reverse
SCR?
biased mode, sir.
Yes, sir.
SCRs are reverse biased. ठीक है? Before theta 1, the supply voltage is less than E. Before theta 1, the supply voltage, and on this SCR, at the anode you have the supply voltage, and at the cathode you have E. So for omega t less than theta 1, since the supply voltage is less than E, or anode voltage is less than the cathode voltage, SCRs T1, T2 both are reverse biased. But there is a condition here. What is that condition? What is the condition? You have studied power electronics, na? Power electronics, advanced power
Yes, sir.
electronics.
Yes, sir.
क्या क्या पढ़ लिए? चलो बताओ जल्दी. What is the condition?
So which type of conditions?
Sir, anode current should be less than the holding current.
Condition means the statement that I just said, that for omega t less than theta 1, SCRs T1 and T2 are reverse biased. This statement is not always true. There is a condition there. Only if that condition is satisfied, then only this statement is
Sir,
true.
alpha should be greater than theta 1, sir. Sir, forward blocking mode is in forward blocking mode, sir.
The condition is that the armature current must be 0. है ना? Yes or no? Because if
Sir,
the armature current
sir.
is not 0, हाँ बोलो कौन
Sir,
विक्रम है?
yes, sir. Sir, armature current should be the effect of, sir, switching off the switches, sir. Why, sir, it is acting as a cause, sir?
ठीक है, I am coming there. If armature current is not 0, if armature current is flowing, then there is a voltage across the inductor. Correct? Yes?
Yes, sir. Yes, sir.
Yes, sir.
Yes.
And what will be the polarity of that voltage? Because at this instant, most probably the armature current is decreasing. Okay? The armature current is decreasing. So the polarity of this inductor voltage will be such that it will forward bias the SCRs. Okay? Now am I clear?
Yes, sir. Inductor will act as a source, sir.
Yes. So this condition that alpha should be greater than theta 1 or the SCRs are reverse biased before theta 1, this condition holds true only when you are starting the motor. Okay? In the first cycle. After the first cycle or in steady state, if the conduction is continuous, then the SCRs can become forward biased even before theta 1. Okay? Is that clear?
Yes, sir. Yes, sir.
ठीक है. Okay, तो कहाँ थे हम?
Sir, all the problem is just due to, sir, inductor, sir. If you remove inductor, then it will be all right.
Yes. That is why you can neglect inducting. Lot of what do you say? Studies you neglect the inductors.
Yes, sir.
But here you cannot neglect the inductance. Everything will be wrong then. Okay, so let us say this is your firing angle alpha. Okay, where the CRs T1 and T2 are triggered. And 180 degrees after that, or at pi plus alpha, you will trigger the SCRs T3 and T4. Okay. So here we are triggering T1, T2. They are forward biased. They start conducting, and because as soon as they start conducting, the armature voltage becomes equal to the supply voltage. Okay. Till when will T1, T2 conduct?
Theta 2.
Till when will T1, T2 conduct?
Omega t plus alpha.
Pi plus alpha.
Sir, it is a continuous mode of conduction, sir.
Theta 2.
Theta 2. ये कौन है जो थीटा 2 बोल रहे हैं, इनको और बहुत पढ़ने की जरूरत है. ठीक है. The question is very simple. The answer is also very simple. Till when will T1, T2 conduct? The answer is till their current becomes 0. Okay? Till when will T1, T2 conduct? Till their current becomes 0. Is it clear?
Yes.
Yes. When will the current of T1, T2 become 0? Two possibilities.
So when the So when inductor completely discharged, sir.
Yes, either when the load current or the armature current becomes zero. That is the first case. Second case, if you have gone into the negative half cycle and you turn on T3, T4. Correct? The current through T1, T2
Yes, sir.
will become zero in two cases. Either the armature current becomes zero, that is the first case, or second case, armature current is still flowing, but you turn on T3, T4 in the negative half cycle. In that case also, the current through T1, T2 becomes zero and they stop conducting. Okay. So, till when T1, T2 conduct, for that we need to know the waveform of armature current. So first we'll draw the waveform of discontinuous conduction. So here initially the current was zero. When T1, T2 started conducting, the current is increasing gradually. Why gradually? Because there is an inductance there. If there had been no inductance, the current would have increased instantaneously. Okay, clear? Yes?
Yes, sir.
Yes, sir. Yes, sir.
So the current will increase gradually and it will lag behind the voltage. Lag behind the voltage means the peak of voltage will come first. The peak of current will come afterwards. Voltage will become zero
Afterwards, yes.
first, current will become zero afterwards. Okay, is this clear?
Yes, sir.
Okay. So
Yes, sir.
as long as armature current is flowing, T1, T2 will continue to conduct. Why? Because of the voltage across the inductance. And as long as T1, T2 are conducting, the armature voltage is equal to the supply voltage. At this instant, the current becomes zero. T3, T4 are not yet on, so all the four devices are off. So the armature voltage becomes equal to E. Okay? Yes?
Yes.
Yes, sir.
At pi plus alpha, we turn on T3, T4. Instantly, the armature voltage jumps to minus Vs. The current cannot jump instantly, it increases gradually. As long as T3, T4 are conducting, Va is equal to minus Vs. After 2 pi, I can come back to 0. Can I? After 2 pi, can I come back to 0?
Sir, there is E, sir.
No. The question I'm asking is 2 pi के बाद मैं 0 पे आ सकता हूँ क्या? इसके बाद का जो वेव फॉर्म है वो मैं यहाँ बना सकता हूँ क्या?
Yes, sir. It will repeat itself.
Yes, because it is cyclic in nature, है ना? ठीक है? So after 2 pi, I can come back to 0. So this part I've drawn here. So as long as the current is flowing, VA is equal to minus Vs. As soon as the current becomes 0, all four devices are off. So VA becomes equal to E. And as soon as you turn on T1, T2, VA jumps to Vs. Okay? Any doubt about these waveforms?
No, sir.
No. Okay. This angle is the firing angle alpha. This angle is the extinction angle beta. This is again the firing angle pi plus alpha and so on. Okay. This armature voltage that you are seeing, is it DC? Is it DC?
DC with ripple.
No, sir. No, sir.
Yes, it is
One
DC
way
with
voltage DC.
ripple. DC with ripples. Or if we apply the Fourier analysis here, okay, we will find that it has a DC component as well as a number of AC components. Correct? What will be the frequency of those AC components? What is the ripple frequency here?
So same
Sir,
like supply
every odd
frequency.
harmonic. Every odd harmonic, because it is a
No. My question is, what is the ripple frequency here?
Sir, 2 fs.
Yes, it is
Yes,
2
sir.
times
Yes,
the
sir.
supply frequency or 100 hertz. Okay. So
Sir,
whenever we are
in one
using a
period, sir,
rectifier,
ripple is coming twice, sir.
whenever we are using a rectifier, we also need to use a filter. Okay. To filter out these ripples. If you are using a single phase rectifier, you will need a very large filter because the ripple frequency is very small. However, if you increase the number of pulses, and this is a 2-pulse rectifier. If you go for a 3-pulse rectifier, that is a 3-phase half-wave rectifier, the ripple frequency will be 3 times the supply frequency. If you use a 6-pulse rectifier, that means 3-phase fully controlled converter, then the ripple frequency will be 6 times the supply frequency. So as you go on increasing the pulse number of the rectifier, filtering out the ripples goes on becoming easier and easier. Okay. In applications or in high power applications where filtering would be an issue.
Sir,
yes.
sir, if the number of times ripple are coming will increase, sir, then sir, how it will be easy for us to remove, sir?
Which filter you will use here? Low pass, high pass, band reject, all pass, all reject. Which filter
So
you will
low
use
pass
here?
filter.
Low pass
So low pass filter.
Okay. So as you go on increasing the cutoff frequency of that low pass filter, the size of the filter goes on decreasing. Am I correct? Am I correct? Yes or no?
Yes, sir.
Yes,
Yes,
sir.
sir.
है ना?
Yes, sir.
The inductive and capacitive components, their size goes on decreasing. Okay? The cost also goes on decreasing. So as you increase the ripple frequency, your ripple cost and size decreases. Okay?
Sir. Sir.
बोलो.
So the same question was asked, sir, in my interview, sir. I couldn't answer this question, sir. So can you please, sir, explain, sir, why sir size will decrease? Sir?
After the class, I'll close off the recording and then I'll explain to you. Okay?
Okay, sir. Thank you, sir.
Sir, so you are saying means ripples means means third harmonics means when we are going to increase the number of harmonic means 11 harmonics or more 17 harmonics. So that harmonics can be easily removed.
Yes.
So their filter size will be small as compared to small harmonics.
Yes. ठीक है. देखो, I'll stop the recording here. We will continue this topic in the next class and we'll talk about filter now. ठीक है.